Hi, my name is dr. Ahmath. In this video lecture, we are going to discuss about the rank of a matrix. So the rank of the matrix is going to tell us the true size of a system of linear equations. And what does it mean is that essentially if you have some matrix A, let's say with the 3 columns, it means that your variable x is going to also have the 3 components, x1, x2, and x3. Okay, so essentially you're multiplying the matrix A to the vector with the 3 components. Does this mean that the column space of your matrix A has the 3-dimensional space? So let's try to understand what does it mean, this dimensionality, and what does actually tells the rank us about the matrix. So I'm going to start with this example of this XY plane. And on the XY plane, we have this 2 really famous popular vectors, I and J. So they are called like the standard unit vectors. So they're called the standard unit vectors. So let's say this is 1 and this is 2, because you can express any vector on this plane, XY plane, as a linear combinations of these 2 vectors. For example, you can just express this vector, let's say this vector was the components 2 and 1, okay, because this is 1 here again, using a combination of these 2 vectors. So what you have to do is essentially you need to scale the I up to 2, so this is going to be 2i. So you need to just get the j and just add them. So if you add them, you're going to get essentially this vector. So this is going to be 2i plus the j. So and in the same manner, we can express any vector on this plane using this combination of these 2 vectors. So that is why we say that, hey, dimension of this xy plane is equal to the 2, because you have these 2 vectors which are required to express all of the other vectors. So this is what does it mean dimensionality. So this is like minimum amount of the vectors which you need in order to express the whole space. So a good example to understand the spaces and the dimensionality of the spaces would be the null space. So the null space of any matrix is defined as a set of all of these vectors x, so that the multiplication of the ax is equal to the 0 vector. So technically, how we're going to find this, we are going to find the special vectors or special solutions, and we are going to take the all possible linear combinations of those special solutions to construct the null space. So in this case, you see, so in order to construct the null space, you're taking the special solution 1, you're multiplying this to some constant or parameter t. You're taking the second special solution, I'm just putting the bar in order to describe your, hey, S1 is a vector and T1 is a constant. So times is a tt plus and so on plus sk times is a tk. For any value of the t1, tt, and so on tk from the set of real numbers. So you see, so you are just basically linearly combining all of the spatial solutions in order to construct the whole null space. So we call it the null space has the dimensionality k, because you need k spatial solutions in order to express this. Well, let's consider an example. So let's say you've got this matrix A with the rows 1, 2, 3, 6. It's obvious that one of the rows is dependent on the second, right? So you can just get the second row by just multiplying the first one, 2, 0, 3. So in order to find a null space of this vector, of this matrix, we need to always bring this to the row echelon form. So by just multiplying the first row to the -3 and add this to the second, we can get the row echelon form. It's going to be 1, 2, 0, 0. Well, the column which has the pivot, so in this case, 1 is the pivot, is going to be called the pivot variable x1, and the column which doesn't is going to be called a free variable x2. So we essentially are going to solve the system. So this system on the first column, which is going to be x1 plus 2x2 is equal to 0. Obviously, it has infinitely many solutions, right? So what we are going to do is we are going to set the free variable to be equal to 1 and plug this to here. And what we get is essentially x1 plus 2 times 1 is equal to 0, or x1 is equal to the -2. So essentially, we are going to get this spatial solution where x1 is equal to the -2 and x2 is equal to the 1. So the null space of this matrix A is going to be the span of simply this vector S1. So simply S1 times the constant T, we call this constant as a parameter t. So this is just behind of the slide. So let's go back to the next slide. So the null space of that matrix has the dimensionality 1 because you need only one spatial solution in order to express the whole null space. So geometrically, I think it's going to be a line, right? So just by combining this vector, you're going to get all the points on the line. So now let's define what is a rank. So the rank of the matrix is essentially the number of the pivots. Okay, so we know the rank of the matrix as R of A, or the rank of the A. So if you look to our previous example, the A with the rows 1, 2, 3, 6, right? So do you remember how many rows, how many pivots it has? So if you bring this to the row echelon form, it has 1, 2, 0, 0. So you see, so this is the pivot. So the number of the pivots is equal to 1. So that's why the rank of this matrix A is going to be equal to 1. So what does it imply? It helps us to construct the null space, or it helps us to understand what is the dimensionality of the null space, what is the dimensionality of the column space, and so on. So this is one of the important parameters, one of the important features of the matrix. So let's try to, in this lecture, I think we are going to try to reveal some technical properties of the ranks, and we'll discuss about the full column rank or full row rank matrices and so on. So let's say we are given this matrix A. So let's find what is the rank of this matrix. So you see, so at the first glance, it is not so easy to see, not always at least, to see what is the rank of the matrix. So if you would like to find the rank of the matrix, you're probably better to bring the matrix into the row echelon form, and you're going to see the pivots right immediately from there. Okay, so in order to do this, again, you're going to choose this element from the first row, and you're going to just eliminate everything below this. You multiply the first row to the -1 and add this to the second. You multiply the first row to the -1 and add this to the third one. In order to get the following matrix, it's going to be 1, 1, 2, 4, 0, right? It's going to be 1, 0, 1, 0, 2, 0, 2. Nice. Okay, so this is going to be the pivot, one of the pivots. Now we're going to go to the one row below. It's going to be this element, the first non-zero entry on the second row. And I'm going to eliminate everything below this by multiplying the second row to the -2 and adding this to the third row. We are going to obtain the row echelon form of this matrix in the form of 1, 1, 2, 4, 0, 1, 0, 1, 0, 0, 0, 0. Well, you see, so this matrix has 4 columns, but only 2 pivots. So the number of the pivots is equal to the 2. So that is why we say that the rank of this matrix A is equal to the 2. So what does it imply for us is that hey, so the column space, if you remember, the column space of the matrix is the all possible linear combinations of the columns of the matrix. But you see, so only 2 of the columns have the pivot. So it means that only 2 of them are independent. It means that it is just necessary for us to combine these 2 columns in order to get the others. Let's see how we can do this. So let's say we are given again this matrix. We say that, hey, the first 2 columns are going to be called the pivot columns because they have the pivots, right? When you bring the matrix into the row echelon form, they are going to have the pivots. And the last 2 columns are going to be called the free columns. So these 2 are going to be called the free columns. And these 2 are going to be called as the pivot columns. So they're called the pivot columns because you can express the free columns as a linear combination of the pivot columns. Okay, so essentially, it is possible to create the column space of this matrix A by just spanning of these 2 pivot columns. So essentially 1, 1, 1, 1, 2, 3. Because this column, the third column, for example, is already going to be inside the column space. So you can express the third column already by combining these 2 first pivot columns. So let's see how we can do this. Oh, I think it's more or less obvious, right? You can get the third column by just multiplying the first one to the 2. And a complete linear combination of getting the third column using the combination of the first 2 would be you multiply the first column to the 2 the second column you're going to multiply to the 0, and if you combine them, you're going to get exactly the third column. Now, what I want is, I would like to figure out a combination of the 4 columns of this matrix, which is going to give you this 0 factor. Is that possible? Yeah, probably yes. So I'm going to just multiply the third column to the 1, and I'm going to put these 2 pivot columns with their coefficients to the left-hand side. So let me denote this column as the third column C3. So this column is going to be denoted as a C1, and this column is going to be denoted as a C2. What is this fourth column? The fourth column is also here, so you can write as 4, 5, 6, which is multiplied simply to the 0, right? So it's going to be C4. Is that true? Right? So we've got the third column by multiplying this first one to the 2, second one to the 0, and the third one to the and the fourth one to the 0. I'm going to put all of this combination to one hand side, right? If you put all of these combinations to one hand side, what we get on the other is simply the 0 factor, right? Which brings you to the spatial solution essentially, right? What does it mean? It means that if you combine all of these coefficients, -2, 0, 1, and 0, and if you multiply this to the matrix, -2, 0, 1, and 0, this will lead to the simply 0 vector, right? Do you remember that we can multiply this matrix A to this vector X as a combination of the columns, where the coefficients of this combination are coming from the components of this vector X. And this is equal to the 0. It means that this is one of the bases or one of the spatial solutions of the null space, because it makes the multiplication AX to be equal to the 0. Okay? So now let's see how we can express the last column, the fourth column, using the combination of the pivot columns again. So again, I see that I'm going to get these 2 pivot columns. Okay, if I multiply the first pivot column to the 3 and the second pivot column to the 1, so what we get is essentially the last column, the fourth column, right? And again, I'm going to just multiply this column, the fourth column, to the 1, okay? And I'm just going to put these 2 pivot columns to the left-hand side, to one side. If we put this again to one side, what we get is essentially 0 vector on the other side. So I'm just going to put the third column. So here you see, so this is the first column, C1. This is the second column, C2. They are the pivot columns, okay? And the idea was like, hey, so you just need them in order to express the column space, because all the other columns, the third column and the fourth column, can be expressed already by the combination of this by the combination of this first 2 columns. So essentially, third column and the fourth column doesn't really add anything to your column space. So this is going to be the third, fourth column, right? And the third column is not here, so we can just artificially add this by just multiplying this to the 0. So that it is going to be here now, okay? The reason why I wrote this here again, so you've got this vector -3, -1, 0, and 1. Exactly the combination of the columns of the matrix A, which makes which creates the 0 vector. Okay, so this is going to be now our second spatial solution. And again, so if you remember, the null space is containing all of the vectors, which makes the multiplication of the A to the X to be equal to 0. So essentially, you are looking for the combinations of the columns of the matrix A, which makes this 0 vector. Okay, and I found these 2 combinations. So the first combination is essentially going to be -2, 0, 1, and 0. And if you multiply this, you're going to get exactly 0, 0, 0, 0. And the second combination is going to be -3, -1, 0, and 1. And this is also makes this 0, 0, 0, 0. So I think we can discuss this features a little bit in more details, right? So you see, so here, the rank of the matrix A is equal to the 2, right? So it has 4 columns, okay? But only 2 of them have the pivots, okay? So that is why the dimension of the column space of this matrix A, essentially, do you remember how many vectors you need in the column space? Only the first 2, right? So by just combining the first two, you can get all of the other combinations of the columns of this matrix A. So that's why dimension is equal to the 2. So now, how many spatial solutions it has? The number of the spatial solutions is always about the number of the free variables. So this matrix has 2 free variables. So this are the x3 and x4 are going to be called the free variables, okay? And you can find this by subtracting the rank from the number of the columns, okay? So the rank is 2, number of the columns is 4. If you subtract them, you're going to get 2. It means that you are going to have 2 spatial solutions. So that is why dimension of the null space of this matrix A is going to be equal to the 2. And here are these 2 spatial solutions of the null space. You see, so the rank is already telling you the dimensionality of the column space and the null space. So let's try to reveal a little bit more theoretical. So let's go a little bit more theoretical, deeper into the topic of the rank. So we are going to classify the 2 different the spatial type of the matrices. The one is called like a full column rank matrix. So essentially, if you're given some matrix A with the k rows and n columns, it is say that to have the full column rank if the rank is equal to the number of the columns. So essentially, all of your columns are going to have the pivots. Okay, so does it mean that this is super good matrix? Oh, yeah, well, no, yes, mostly, yes, it's a good matrix. If your matrix is the square matrix, so essentially the number of the columns is equal to the number of the rows. So the fact that all of the columns have the pivots, it means that all of the rows have the pivots as well, right? Because the number of the columns is equal to the number of the rows. But it is also possible that you're going to have this kind of matrix. Okay, so for example, with only 2 columns, but many rows, maybe 10 rows, right? Obviously, one row cannot have more than 1 pivot, okay? So that's why, like in this case, you're going to have lots of rows without a pivot. And now let's try to reveal what basically implies this fact that many of the rows of the matrix do not have the pivot. So well, it appears it implies the following conclusions. So since all of the columns have the pivots, then there is no free variables. If you remember, the number of the free variables is the number of the free columns, right? So if all of the columns have the pivots, there is no free variable. It means that the null space of this matrix is going to contain only 1 vector, which is going to be the 0 vector. So what does it mean? It means that the system AX is equal to the 0 is always going to have a unique solution, the trivial solution, because there is no special vectors. Okay, you remember the null space was always the span of the spatial solutions S1 and so on Sk plus the 0 vector. Okay, and in this case, there is no special solution, so that's why the null space is going to contain only 1 0 vector, which is going to be the trivial solution for the homogeneous system of linear equations. Well, if you are given non-homogeneous system of linear equations, then the number of the solutions is going to be either unique solution, either no solution. So let's consider an example of the system when it is going to have, for example, a unique solution. So this system, for example, has always a unique solution, no matter what is the b. So if you would like to write down the system of linear equations, AX is equal to the B, it is always going to have the solution. So could you please try to pause the video and try to answer why the system has always the solution, always a unique solution? Okay, so here you see, so this matrix already is given in the row echelon form so that you can see the pivots already, right? It has 3 columns and all of the columns have the pivots, okay? So it is the full column rank matrix. So the number of the columns is equal to the rank of this matrix A. Okay, so this is called a full column rank. So well, this matrix has, so the system AX is equal to the B has always a unique solution no matter what is the B, because A is invertible, right? So the determinant of this matrix A, since this is the upper triangular matrix, so it's going to be just the multiplication of its diagonal entries. So it's going to be 1, 1, 1. It's going to be simply equal to the 1, which is not equal to the 0. It means that your matrix is going to have its inverse. So then if you are given the system of linear equations AX is equal to the B, no matter what is the right-hand side part B, you can always multiply both of the sides to the inverse of the A and get the solution X. It's going to be simply A inverse times to the B. Okay, so this is the case when the matrix is going to have a unique solution when it has the full column rank. But everything is not so easy. So if your matrix is in this form, again, it has the full column rank, it is not going to have the solution at all. So let's check how it is possible. In order to do this, I'm going to put both of these matrices into so-called augmented matrix and bring that matrix into the row echelon form. So it's going to be 1, 3, 2, 2, 5, 4. Then I'm going to put the right-hand side part 1, 2, 3. Okay. So I'm going to eliminate the 3 and 2 by multiplying the first row to the -3 and adding this to the second. By multiplying the first row to the -2 and adding this to the third row, we are going to eliminate those entries. It is going to be 1, 2, 1. So it's going to be 0. 2 times to the -3 plus 5 is going to be -1. 1 times to the -3 plus 2 is going to be -1. Okay. Then I'm going to multiply the first row, all of the entries on the first row to the -2 and add this to the last row. It's going to be 0, 0, and 1 times to the 3, 1 times to the -2 plus 3, it's going to be 1. Okay, well, the system has no solution. It's clear from the last row, right? The last row tells you that, hey, multiply 0 to the first variable x1 plus 0 to the x2, and this should be equal to the 1, which has no solution. Okay, so this is what does it implies. Like, hey, if the column space, if the essentially your matrix has the full column rank, then either it has the unique solution, either it has no solution. But its null space is also going to have only the trivial solution. This is like the properties of the full column rank matrices. But again, so there are the second type of the matrices, the special matrices, are going to be called like a full row rank matrices. So what does it mean? That, hey, if you're given the matrix A with the k rows and n columns, then the number of the rows, the number of the pivots is going to be equal to the number of the rows. It means that all of the rows are going to have the pivots. And again, if your matrix is square, it's super clear that if all of the rows have the pivots, it means that all of the columns have the pivots as well. Okay, so it's going to be a really good matrix, invertible matrix. You can solve the system of linear equations always. It's going to have a unique solution and so on. And if your matrix is given like this, so let's say like with only 2 columns, 2 rows, both of them have the pivots, but lots of columns. Obviously, the columns cannot have more than 1 pivots. Okay, so it's like, or the rows cannot have more than 1 pivots. So that's why some of the columns are not going to have the pivots. Okay, so let's see, what does it imply? Does it imply that your system is not going to have a solution again or not? Okay. Okay, so what does it imply? It implies that the full row rank means all of the rows have the pivots. So the system of linear equations AX is equal to the B has the solution always, no matter what is the B. So it's always going to have a solution. If it is square matrix, if the A is a square matrix, then the system AX is equal to the B is going to have a unique solution. If it is a rectangular matrix, then it's going to have the infinite solutions. Okay, so let's see why. So the number of the special solutions is obviously going to be n minus k. So in this case, if your matrix is rectangular, for example, if your matrix has 3 rows and 5 columns, okay, the number of, so your matrix now is given as a full row rank. It means that the number of the pivots is equal to the 3. All of the rows are going to have the pivots. Okay, what does it mean? It means that only 3 of the columns out of 5 are going to have the pivots, because the pivots cannot be more than 3. Okay, so and it means that 2 of the other columns are going to be the free columns. Okay, so which implies that the number of the special solutions is going to be 2, which can be found by subtracting the number of the rows from the number of the columns, right? As we have here. Okay. Cool. So let's do an example again. So here, this is an example of the matrix with the full row rank. So we've seen this before already that, hey, so all of the rows here, the first, second, the third row have the pivots. So the pivots, since your matrix is a square matrix, it has 3 rows and the 3 columns, square matrix, any system of inequations, AX is equal to the B, is always going to have a unique solution, and this unique solution is equal to the A inverse times the B. Okay, but at the same time, if it is given that your system of inequations is given like this, your matrix C is given like a 2 by 3 matrix. So it has the full row rank. Most of the rows have the pivots. In this case, your system of inequations is going to have infinitely many solutions. So let's see why. So essentially, so it's like, you see, so 2 of the columns already fill the column space. The third one is extra. Okay, so that is why it's create like infinitely many solutions. So this is like essentially the reason why we have the infinitely many solutions. So let's see technically how this happens. Okay, so I'm going to create augmented matrix 1, 2, 3, 5, 2, 4, and then 1, 2 again. Okay, so we need to bring this matrix into the row echelon form. I'm going to multiply the first row to the -2 and add this to the second. So the first row is going to be multiplied to the -2 and add it to the second. And what you have is essentially 1, 3, 2, 1 is going to be 0, and it's going to be -1, right? Then it's going to be 0 again, then it's going to be 0. Okay, cool. Like I can multiply, for example, the second row to the -1 and get 1, 3, 2, 1, 0, 1, 0, 0. Okay, so you see, so I've got 2 pivots, this column, and this column. So both of the rows have the pivots, but only the first and second column have the pivots. It means that the third column is going to be the free variable. Okay, it means that it has an infinitely many solutions. So the system has infinitely many solutions. And if you remember, we discussed about the constructing the complete solution, right? The complete solution is going to be the particular solution, okay, plus the span of the null spatial solutions. In this case, you are going to have only one spatial solution. So here is an example of a matrix which has the full row rank, which has infinitely many solutions for any system of inequations. AX is equal to the B. Okay, so this is about the rank. So in our next video lectures, we're going to talk about the independence and dimensionality, which is coming from the rank. So far that's it. So thank you very much for your attention. Hope that it was helpful.